Hi, I'm Evan Wallace, President of Applied Physics. In this demo, I want to explain at the molecular level how open bottles of champagne can be kept at equilibrium and not lose their effervescence. Along the way, we'll discover an important principle of physics and chemistry called Henry's Law. This simulation represents a sealed bottle of champagne. The blue region here is the liquid, and the gray region above is the headspace above the liquid. Right now there isn't any gas in the bottle, so we're going to add some. I can add two types of gas A or gas B, to either the headspace or the liquid, depending on where the plus sign is, above or below the liquid-gas interface. I'm going to call the red molecules here our carbon dioxide, and I'm going to add 100 molecules to the liquid. I'm going to click once, that adds 50, and click again, that adds 100. Now I've got the surface of the liquid sealed, so I can get my molecules added and set the timer at 0. And now we're going to open the surface and let the molecules diffuse out of the liquid. So open surface, and here we go. And you can see the molecules coming out of solution and going into the headspace. Some are in the headspace and diving back into solution. And you see the numbers changing here. This is the number of molecules in liquid. This is the number of molecules in the headspace. And this tile right here is measuring the partial pressure of CO₂ in the headspace. You see it just turned red. That means equilibrium has been reached, which means that the pressure of the CO₂ in the headspace is no longer changing radically. It's essentially settled down. Now, because I'm using so few molecules, just 100 as opposed to many, many billions of billions in real life, that would be something the size of a champagne bottle, the pressure jumps around a little bit, it's a little jumpy. If I had many billions of molecules, the pressure would be very smooth. The thing I want you to realize here is that at equilibrium, where this pressure here is essentially the same from moment to moment, it's not that nothing is happening. A great deal is happening. Many molecules are moving from liquid to gas, and many molecules are moving from gas to liquid. It's just that at equilibrium, those two rates are equal. So now the question is there some other way that we might be able to keep CO₂ in solution? Is there a way we could do it with some other gas? So we're going to try it with gas species B, which I'm going to call argon. So we're going to go back and do the same thing. We're going to add our 100 molecules of CO₂ to the liquid. Now I'm going to add 100 molecules of argon to the headspace. And let's see if the argon will actually, quote, keep the CO₂ in solution. Let's open up the surface and see. We'll let the system evolve to equilibrium. And there we go. CO₂ molecules the number in solution is going down, the number in the headspace is going up. And we'll look at the partial pressure going up, 45, 46, 47, which is about what it was with no argon. And there we see the tile turning red, right at about the same pressure, right around 50 psi. So the argon made no difference at all in keeping the CO₂ in solution. It was just as if it weren't there at all. In fact, I can tell you that even if we had 1,000 psi of argon in headspace, it wouldn't keep one more CO₂ molecule in solution. Only CO₂ can keep CO₂ in solution. Now let's do another variation on this theme. I'm going to put my 50 CO₂ molecules in solution here, and then ask the question, what do I have to do to keep those 50, that concentration of 50 molecules in solution? We saw that argon didn't do anything. Let's try CO₂. Let's add 50 molecules of CO₂ to the headspace. And now when I open the surface and let the system evolve, it is essentially already at equilibrium. Watch this tile, it turns red. It goes to equilibrium almost right away. So that's how you keep CO₂ in equilibrium with more CO₂. No other gas will do. Not a million psi of argon would keep even one molecule of CO₂ in solution, because it's not the gas in the headspace that, quote, keeps the gas in solution. It's the CO₂ in the headspace is simply balancing the rate of efflux of CO₂ from liquid to gas. So no molecule is keeping any other molecules anywhere. It's simply balancing the rate of efflux and the rate of solution. And now, of course, if we were to pop the top of the champagne bottle, remove the cork, then we're going to let all that gas in the headspace go away. And now the gas in the headspace isn't keeping the gas in solution any longer. It's not balancing the rate of efflux of CO₂ from solution to gas. And you see what happens. Your champagne goes flat, one molecule at a time, just as it does in real life. Well, I hope you'll give the simulator a try and try playing around with it on your own. It's available at the link below. And thank you very much for watching. We'll be back next week.